Good morning. Thank you for coming so numerous today. I'm going to talk about something rather different than the other speakers. So far, the focus has been on computational efficiency and on how to address really large data sets. And I would like to venture into a different area, which is what is it that we are going to do with all this big data? So we used to, in the days, before machine learning, to worry mostly about explaining data. So building explanatory models, descriptive models. And now, with the advent of machine learning, we started venturing into forecasting, into building predictive models that can do things like what we've seen before, like recognizing digits or interpreting images. But we're still staying within the realms of what statisticians call IID data, which are data that are independently and identically distributed, which means that the distribution don't change over time. However, in the real world, things change constantly. And in particular, what we would like to do is to allow these models to help us make decisions. Decisions about what we should do to make the world better, what we should do to prevent catastrophes. And as soon as we intervene on the model, then data are not IID anymore. The distributions change. So this is what I'm going to talk about. What is going to change when we move from models that are merely predictive to models that allow us to have some decision power, to allow us to predict not only just what the next observation is going to be, but what's going to happen if we change something, if we intervene on the model, if we change policies. So this is illustrated in many aspects of the big data adventure that we are going through. Data is all interconnected. It's not just about putting some input on one side of the machine and finding some output. All the variables are interconnected. So this is seen, for example, in gene networks. All the proteins that are produced in our body are triggered by gene transcription and then protein translation. And all of the chemicals that are running in our blood are just all interconnected. So in order to predict what influences a drug has when you take it, you need to understand a whole lot of things. Then there are other types of networks in biology, like neural networks. What's going on in our brain? In our brain also, each little neuron is a little function that takes in inputs from other neurons and outputs, some signals, and all the signals are interconnected. So understanding how the brain functions requires also to have some models that don't just make predictions, but have some causal flavor to them. We have also other networks that are social networks. We have climate networks. We have networks between countries. So all of these networks need some understanding. And the prime setting that we have here, from the mathematical point of view, is that we have a data matrix, like you see in regular machine learning problems. The rows represent samples, and the columns represent features. So this is your regular data matrix. But what we want to do here is to be able to produce a graph, which means that each variable interacts with another variable. And each node here represents one of the columns of the matrix, so one of the variables. And each link means that there is a direct causal effect between one variable and another variable. And so the output of the learning problem here is an adjacency graph. So you see, I'm not sure I have a pointer on that. So the matrix that you see called the output has a 1 if variable A is connected to variable B, for example, and a 0 otherwise. So it's a different kind of a learning problem. So causal questions are pervasive. They have to do with what affects your health, the economy, climate changes. But the main questions are which actions will have beneficial effects. So in order to answer these questions, traditionally, people use the scientific method. And it consists first in observing correlations, then hypothesizing causal relationships. For example, a variable A is causing a variable B, or B is causing A. Or there is a common cause C to A and B. These three cases could explain a correlation. And in order to disentangle this problem, you perform experiments. But unfortunately, not all experiments are possible, and experiments are often costly. They may be unethical, and there is at any rate always a cost to an experiment, and this is why you want to prioritize them. So as the first step, you observe correlations. So we owe this nice example to a paper that appeared recently in the New England Journal of Medicine, where a correlation has been evidenced that there is a connection, presumably, between eating chocolate and earning a Nobel Prize. At least what we see is that among the various countries around the world, there is this correlation between chocolate consumption and the number of Nobel Prize per capita. So is this good news? Well, some companies jumped on it right away. Eating chocolate produces Nobel Prize winners, study. But immediately thereafter, on the internet, you could see other interpretations. Chocolate and Nobel Prize in study. Geniuses are more likely to eat lots of chocolate. So what is the correct explanation? There are several hypotheses. Chocolate causes Nobel Prize, Nobel Prize causes chocolate, or neither. There could be a third explanation to this correlation. There could be a common cause. For example, GDP per capita could be causing both. Being able to have better access to chocolate or better access to education. Or it could be coincidental. Maybe there was not enough data to support the study. So the answer to disentangle this problem is to conduct experiments. Experiments are not that easy. Notice that the Nobel Museum also made some money on immediately issued chocolate coins. So you could run the following experiment. Test your researchers for 10 years. Randomly pick half of them and give them chocolate for dessert, and give apples to the other half, and compare, which half earns more Nobel Prizes. You can see immediately that such experiments are not so easy to perform, so eventually you have to perform these experiments, but you want first to do everything you can to prioritize them to reduce your cost. So when we get, all these very interesting big data sets, we can venture into making interpretations, looking at the meaning of the variables. And you could, venture into thinking that perhaps smoking causes lung cancer, pollution causes climate changes, education causes crime rate, alcohol consumption, car accidents, etc., just by looking at the names of these variables. Can you do a little bit better than that? Can you look at the data and using some simple statistics, score all these pairs of variables and say which ones you should, test first in an experiment? There is a lot of work in the literature that has been going on since the 1980s, starting with some pioneers like Limor China's Spiritus and Pearl, who recently won the Turing Award, Rubin and also in the US. And then there has been a new wave coming from Europe. We've had Hiverinen, Shalkov, Bullman, and others come up with novel algorithms actually using machine learning. And we have attracted some attention to that field with several Nobel Prizes in econometrics. And recently, DARPA has started pouring some money into the subject, so hopefully this is going to make big steps now. And you may wonder what ChaLearn is about. So ChaLearn is a company that I started. It's a nonprofit. And ChaLearn organizes challenges in machine learning. And we've been using that as a tool to advance science. This is because essentially, after having contributed algorithms in my youth, I think now that there are so many young, talented people around, there's a much better chance that they're going to make the next new contribution than I do. So I like formalizing problems and letting you guys solve them and make these great new contributions. So since 2007, we've been organizing challenges on causality. And I will be talking to you about one of them in particular. So to make a long story short, what did we learn with these challenges that we organized? The first thing we learned is that discovering dependencies is the easiest part of this problem. A dependency is a little bit a generalization of a correlation. So correlation essentially measures the linear dependencies. You can have nonlinear dependencies. Also, you can have dependencies between multiple variables. But this is all classical statistics. This is all fairly well understood. And we have been working before we ventured on working on causality on the problem of feature selection, which is still hugely important, but essentially tries to uncover dependencies between variables. And this works really well, and it's hard to beat with causal algorithms. Which means that if you try to get a little bit better than finding mere dependencies by orienting edges in a graph, then you might actually get worse results than if you just guess the orientation at random and you focus only at finding which are the nodes that are connected. So the second problem is removing spurious dependencies. So imagine that you just know that there are dependencies between two variables. Well, do you know whether this is a direct connection or an indirect connection? So finding out about that is harder. And it's dangerous because eventually you're going to be removing too many connections. And so it's going to be more harmful than useful if you try to make predictions. But the hardest of all problems is orienting the dependencies. And so I'm going to be talking about that today. We worked on that by organizing the Causeeffect Perth Challenge in 2013. And I have to be hugely grateful to all of my collaborators. This was a big, big team effort. It started with the impulse given by Bernard Shalkov and his team in Germany. They worked for many years on this cause-effect pair problem, and they gathered the first little benchmark data set. And then I'm also hugely grateful to Kegel and Ben Hamner in particular, who will be talking later today. Maybe he's already in the room. So Kegel hosted the challenge, and Ben himself made some sample code that inspired the participants and also came up with the idea of actually giving training data so that people could solve this problem. So after that, let me tell you a little bit about the problem setting. Before I told you, well, we're going to infer the entire causal network. And the problem is we have this data table, we have the examples in lines and the variables in column. This all looks familiar. And what we want to output is this adjacency matrix. A matrix in which each entry indicates whether a certain variable is connected or not to another one. And the connections should be directed. Now we're simplifying this problem a whole lot. We're focusing only on two variables. And the problem, phrased as a machine learning problem, is whenever you have data about two variables, can we say that A is a cause of B or something else? Something else meaning B is a cause of A, or there is a common cause to A and B, or A and B are not related at all. So it's just a classification problem. And the input to the classification problem is two columns of this data matrix. The output is A is a cause of B or not. Now maybe we overly simplified. Some of you who may be familiar with the problem would think it's crazy because we need to know the context of the other variables to figure out whether there is a causal relationship. We have all these other variables in particular that could be confounders, that could be common causes of A and B, and if we ignore them, we can't say very much. Well, this is precisely why we want to focus on only two variables, because we never know all the possible variables that could be influencing A and B. These are assumptions that people make that are called causal sufficiency. For most algorithms to work, you need to assume that you know all the variables that could possibly influence A and B. Here we don't make this assumption at all. What we have rather is a scatter plot. So here each dot represents one of the samples. So if you have your data matrix and you have each line representing a sample, and we have two variables, A and B, here each point on this plot represents one of the example. So assume that A and B would be the age and the weight of a patient. Each dot would represent a patient. Given a scatter plot like that, can we say whether A causes B or B causes A or something else? So now I'm putting you to work. Now it's a quiz for you. Can anybody think about a reason why we might think that A causes B or B causes A? So in what sense also do we want to say that? So the working assumption here is that we're not even using time. So people often think of causality as something that involves time. But here we're thinking more of causality in terms of a function. Is B a function of A or A a function of B? And we are thinking of a non-invertible function. And this is like what you have when you build a system with gates, for example, in electronics, and you have information flow only in one direction. So the output is a function of the input, but you can't invert the function. So in that sense, would you think that A rather causes B or B causes A? A causes B? Yeah, I hear a lot of A causes B. I hear some of B causes A. So here is the answer. These are two actual variables. A is the altitude of German cities, and B is their temperature. So there is some logical, reasoning that forces us to think that the recorded average yearly temperature must be a consequence of where the city is located and not the other way around. And in order to figure that out, we can do a fit. We can fit A as a function of B or B as a function of A, and we can look at which fit is best in terms of the R-square, for example. And in that case, it's a lot easier to fit B as a function of A than A as a function of B. As a matter of fact, it looks like there is like a little bit of a convexity that is hard to capture as a function. This maybe is a non-invertible function. So the second explanation with the green curve is a lot more justifiable than the first one in terms of residual, in terms of complexity of the model. So researchers have been trying to mathematically capture this idea of there is an easier fit in one direction or better fit in one direction than the other. But the contribution that we've made by organizing this challenge is to give data. We have collected thousands of pairs of variables. Some of them are real pairs from data mining databases. And some of them are artificial pairs. In generating artificial data, we had a lot more control. We could span a broader variety of variables, and we could balance data better than by using real variables. So we used 20% of the real data from pairs that are like age causes wages, or cancer volume when you do surgery may cause or not recurrence. And then we had 80% of artificial variables. Now then the results were really, really stunning. By just giving out to the world training data that people had, for a problem that people had never seen before, we made a huge progress compared to the state of the art. On this graph, what you see is the test error, the success rate in terms of area under the ROC curves, which is a metric for classification success. 0.5 is random guessing, and 1 is perfect. So before we started the challenge, random guessing was 0.5, correlation coefficients would give us a little bit better, independence tests slightly better, and the state-of-the-art methods around 0.6. And after the 267 participants contributed, the winners were reaching over 0.8. And actually, the winner might be in this room because he sent me email saying that he would be at this conference. So Diogo, if you're here, raise your hand. Not yet. So Diogo Almeida won this challenge. And what he did is that he did apply machine learning in a brute force way, generating lots and lots and lots of features of the scatter plots that I have been showing you, and then running random forest. So this is actually a pretty damn hard task. Even today, for other state-of-the-art methods that didn't use machine learning, they don't get very much better than 0.6. Whereas the winners of the challenge got over 0.8. All the scatter plots look very difficult to interpret. And we had continuous variables, categorical variables, binary variables, a wide variety of things. So we can say we have now an operational causation coefficient that can be used to supplement correlation coefficients, and have this additional feature that they can orient edges. I didn't tell you a whole lot about network reconstruction. I focused, about only these pairs, but we did run other challenges. One of them was on unraveling the structure of neural networks, real neural networks, the ones from the brain, for imaging data. And here the prime setting was really similar, except that the rows now representing the samples are time ordered. But the really interesting thing that came out of this other challenge and ties into the first one is that people singled out a method that was published in Nature before that's called network deconvolution, and that allows you actually whenever you start with connections between two nodes, to suppress the spurious connections. So basically, with the method I told you before and this network deconvolution, you have a full methodology. Here on the graph, what you see in a circle are all the nodes, and the edges are in blue in the first column. In the second column, you see the edges that have been inferred by an algorithm that basically looks at pairs of variables. And there are a lot of spurious edges because there are indirect effects. And then after running this network deconvolution, you remove the spurious edges. So it's perfect on the first line because the method has been tuned for linear models. And so it's completely removing the spurious connection in the case of linear models. And in the case of nonlinear models, the second line, it does a pretty good job, but there are a few remaining edges. So what so where we are today is that we have now some tools that allow us to better explain data, and that can be used as part of the decision-making process. I would like to advertise, for challenges as a tool to make progress and boost the state of the art. It certainly worked in the case of causality. the application of machine learning has shown that we could get an operational causation coefficient and integrate it into a consistent methodology. And the last slide is some advertisement for another challenge we are presently organizing. I'm running out of time, so I'll be glad to take your questions during the break. There is a lot, to what I've been talking about in terms of smarts that people have put into solving this very hard problem. Thank you.